Lab 7 deals with an introduction to the software package called Ansoft Designer. Ansoft Designer is a suite of design tools that fully integrate high-frequency, physics-based electromagnetic simulation, modeling, and automation in an environment for circuit and system analysis. In the lab, we're going to be using the student version of Ansoft Designer, which is free and is available on the web. Now, with any robust software package, it's best to start with some known examples and try to recreate them in simulation. This way you can kind of see how our knowledge meshes with the new tool. Maybe we can clear up any misconceptions that we have with what we know and what we're seeing in the simulation. The concepts we're going to cover are the first-time use of Ansoft Designer, schematic creation and parameter adjustment, and creating and editing graphs. The examples we're going to use are the Lab 6 network analyzer plots, input impedance of a coaxial cable with load, and S parameters of a 2-port. To do this lab, you'll need a PC. Our first example with Ansoft Designer will be to measure a long lead resistor like we did in Lab 6. In Lab, we have the student version of Ansoft Designer installed. If you're doing this outside of Lab, please get the program, install it, and then go to step 1, which is to find all programs, Ansoft, Ansoft Designer Student Version 2, and then Ansoft Designer. And then I'll start the program. A new design space will appear like shown here in Figure 1. Now this space is set by clicking on all the boxes under View. On the left-hand side of the screen, you'll see a project window, which is here. In the upper part of the screen, you'll see the word Project 1. Now right-click on this, and then select Insert, and then Insert Circuit Design. It's going to ask you to choose a layout technology, which is used to select a printed circuit board. We're not going to do that in this project, so just click on None. Components can now be placed under the schematic. To see the components, click on the Components tab directly under the Projects tab. And all the available RF components are listed in the project window. We're going to next select an inductor. Inductors are listed under lumped elements. If you expand the lumped elements listing and then expand the inductors, you'll see what's shown here in Figure 2. Now right-click and drag on this IND inductor onto the schematic area. Then hit Escape on the keyboard to end the symbol on the cursor. Now if you make a mistake, just click on the element and hit Delete to erase it. What you'll have is shown in Figure 3. Here's our inductor with a default value of 10 nanohenries. Now next, go find resistors in this lumped element listing and click and drag a resistor onto the screen, but it's going to be the same orientation as this inductor. So don't release it yet. And then to rotate it, just hit R on the keyboard and then it'll look like this, and then hit Escape and it'll place it on the screen. Next, I want to wire up the circuit and put a ground symbol in. Okay, ground symbols are located in the toolbar on the upper left of the screen. To place a ground, click on the toolbar symbol and then click anywhere on the schematic. Now don't do that yet. We're going to do one more thing first. We'll next take a look at how to wire components. So move the cursor on the top of a terminal of a component. You'll see that a symbol X will appear. And by clicking once, the cross symbol will stay there, and you can drag the wire to another component terminal. And then by clicking on that other terminal, it'll make the connection. Now don't do that yet. Let's go back to our previous schematic. Let's place a ground as we described on the last page. Then we can wire these components up. We're going to click here, and it'll make a right angle type connection. Click here, make this connection. We'll click here and we'll put a wire and just let it end here. Just by double clicking on it, it'll release the wire. So now we got our schematic somewhat wired up. Now we got the wrong values here. This is not the value we had in Lab, so let's see if we can change those. If you double click on it, it comes up with a little menu like this, and you can change the value of the component. In our case, we're using a 40 nanohenry inductor. Ansoft specifies sources as well as loads through a port symbol that looks like this. This is located in the toolbar next to the ground symbol. Now place a port symbol at the left end of the long wire from the inductor. If you double click on the source port, it'll open an editing window as shown below. Change the options to a microwave port under Symbol in the upper right hand side of the editing box. That's shown right here. Add a source definition by clicking on the Add button in the source definition box and then type 1 milliwatt, which is 0 dBm for property P. The editing box will look like what's shown here in Figure 6. Now keep clicking on OK until the schematic shows again. The source port symbol will have changed to an AC source with a series resistor like that shown in Figure 7. The term PNUM equals 1 is microwave port number 1. RZ equal to 50 ohms means that the real part is 50 ohms, and IZ equal to 0 ohms means the imaginary part is equal to 0 ohms. Now save your file to the M drive, or if you have an external drive, save it to there. With the schematic built, an analysis profile must be defined, which is similar to adding the .AC line in PSpice. To define the analysis, click on the Project tab in the Project window, expand Project 1 asterisk, then expand the Circuit 1 list, and right-click on the analysis symbol. then select Add Solution Setup, and a new box will appear. Click Next, then click on Add, and then Edit, and then enter the data as shown in Figure 8. We're going to start at 10 megahertz, go to 600 megahertz with 100 points per octave. And we're going to add that, and it puts it over here. And just click on OK. Now the circuit can be analyzed by clicking on the Analyze button, which looks like this, located in the upper toolbar. After the analysis, the results have to be looked at by using the Results option in the project window. So left-click on the results to highlight it, then right-click, and then select Create a Report. A new menu pops up, and the desired response, in this case, is going to be Standard Rectangular Plot, and then click OK. Now I want to put the phase angle of S11 like we did in lab, and this is shown in Figure 9 by selecting S11, and then Angle, and then clicking on Add a Trace, and then click Done. The resulting graph that you should get is a plot of S11 from 10 megahertz to 600 megahertz. It should look pretty similar to what you measured in lab on our network analyzer for the resistor R sub S. Sometimes you want to change scales. In my case, I want to make it look like the graph I actually plotted. So let me do that. I'll start with changing the y-axis. I want to change the scale from minus 10 degrees to 40 degrees. So we'll double-click anywhere on the y-axis, and the y-axis properties box will appear. Click on Scaling and uncheck Auto Scaling. You'll see this box that's over here, and then you can type minus 10 to 40, do 5 minor divisions and 10 major divisions, and then unclick the Show Minor Grid, which is shown here. Likewise, change the x-axis setting from a minimum of 0 to maximum of 600, minor divisions equal to 5, major divisions equal to 10, and uncheck the Show Minor Grid. Your graph will look something like what I have in Figure 11. Now the trace that's shown here is pretty thin, and so I'm going to make it thicker by double-clicking on it, and then select Line Styles, and change the width to 20. This pretty much looks like the picture that I had when I did the lab. Pick the corresponding scales to match what you had in lab. Now in Lab 6, we also displayed the value of the impedance of our resistor, R sub S versus frequency on a Smith chart. We can do the same. So we need to create a new project report. So left-click on Results again, then select Create a Report. Menu will pop up, and pick Standard Smith Chart, and then click OK. Again, we want to plot S11, so select that if necessary, and then click None, and then add a trace, and you're done. The results are shown in Figure 12. Notice that the blue highlighted circle here is a little hard to distinguish. Also, the font size of the numbers inside the Smith chart seem to be too large. So let's see if we can fix that. So right-click anywhere on the Smith chart, and some options will appear. Select Zoom In. To enlarge the area like that's shown in Figure 13 below, hold down the left button of the mouse and drag the square symbol over the desired area and then release it. Now double-click on the blue portion of the 2 ohm circle, which is here, and change the width of the line to 20. Right-click again and select the arrows. Double-click on the resistive circle font and change it to 10 point. Likewise, do this for the reactance arcs, and your plot should look like Figure 14. Next, I'd like to read some numbers off of the graph. We're going to create a data marker. Right-click again and select Data Marker. The highlighted curve will turn to yellow with a marker circle. Right-click again and select Marker Scale, and then select Impedance Scale. Move the marker with the arrow keys to approximately 300 megahertz. The value of S11 is used to calculate the normalized impedance in a rectangular form using equation 2 of Lab 6, assuming that Z0 is 50 ohms. Results are displayed in the upper right corner as shown in Figure 15. Record this and multiply by 50 to denormalize. Here's the value right over here. This is our reading at 296.508 megahertz. This is the closest data point to 300 megahertz. Using the denormalized value, calculate the value of R and L using the actual frequency of the marker, and record this in your lab report. Right-click again and select Exit Marker Mode and Fit All to restore the Smith chart to full size. Print a copy for each member of your lab group and include as indicated in the lab report. Save your project and close it. Next, start a new project, and we're going to take the example that's on page 48 of the Chapter 3 class notes, which is a 1-foot coaxial cable. This is shown in Figure 16 using the components under coaxial cable by selecting Coaxial Reference, Coaxial Cable, K with reference nodes. Now lay out this schematic and double-click on the cable to edit its values. Set the value of P, which is the physical length, to 12 inches. Avoid using feet because there's some bug in the software that deals with using feet, so just use inches. We've also need to set the value of K, which is the dielectric constant for the material that's filling the transmission line. We'll set it to the value of Teflon, which is 2.21. To see more about the model and/or references, double-click the button in the info line under the column value, which has the name of the component. Now save and run this file and display the magnitude and angle of ZN under the Z parameters for a frequency range of 1 MHz to 1 GHz with 1,000 points per decade, and change your x-axis to a log scale. This is the input impedance looking into the cable. We can also mark points on our displayed graph. So left-click on the magnitude graph, and it should turn yellow. Right-click and then select Data Marker. Moving the cursor with the mouse or with the arrow keys, move the marker as close as you can to 0.1667 GHz. A left click will mark the data point with the x and y axis values. The result should look like figure 17. Mark the other points as indicated in figure 17. Here's our values down here. I'll print a copy for each member of your group and include this in your lab report. Save and close your project, and we'll start another one. From our notes on pages 71 to 72 of the ebook in Chapter 3, we have an example of finding the S parameters of a shunt 100 ohm resistor in a balanced system. Figure 18 shows the layout of this system. Here the port symbol is left as a default of interconnect, which means that it is a transmission line terminated in its characteristic impedance, which can be specified by double-clicking on the port symbol. The default is 50 ohms. So lay out this schematic. Now, save and run your file to display the magnitude and the angle of the S parameters for a frequency range of 1 MHz to 1 GHz with 1,000 points per decade. I'd like you to change your scales for the y-axis to match what's shown in figures 19 and 20. Just scroll to that. Here's figure 19, and it's displaying the magnitude of S11, S12, S21, and S22. Now, by clicking anywhere on the graph, you can pick the option of Mark All Traces. What that's going to do is put a dark cursor line right here on the graph, and you can move that around, although the values here are constant, and then it gives the values of S11, S12, S21, and S22 in magnitude, and shows the x and y axis values for the cursor. The same thing is shown here for the angle. You can slide this around up here and move it anywhere on the graph you want, but again, it's just showing here it's constant versus frequency. Now print a copy of both these figures for both members of your lab group and put that as part of your lab report. The remaining part of the lab is having you change some values on the schematic. I want you to take a look at that. But this is the first time use of Ansoft Designer for Lab 7.